So in this video we're going to go over how to find the equation of a tangent plane to a surface in space. So what we want to do is recall the general formula for a plane in three-dimensional space. And this was a formula that we developed earlier in the semester. And what we discovered is that if we wanted to find the equation of a plane that contained a point x naught, y naught, z naught, that we just needed to find a vector that was perpendicular to the plane, a vector ABC that was normal or perpendicular, and we took the dot product of the normal vector with the vector that looked like x minus x naught, which is a vector in the plane. So x minus x naught, y minus y naught, y minus y naught, z minus z naught was a vector in the plane, and then we took ABC, which was a vector perpendicular to the plane, and we recognized that the dot product of perpendicular vectors had to equal 0. And so when we took this dot product, we wound up with the general equation of a plane. So the key idea here is that to find the equation of a plane, we need a vector that's perpendicular to the plane. And when we're looking at a surface in space, when we're trying to find a tangent plane to a surface, then what we would need is a vector that was perpendicular or normal to the surface. So if we want to find the equation of a tangent plane at the point x naught, y naught, z naught, we know that we can construct vectors in the tangent plane just like we do here, x minus x naught, y minus y naught, z minus z naught. But we need a vector that's perpendicular to the tangent plane. And what we discovered was that for any surface S, we could come up with a function big F of x, y, z equal to 0 that represented that surface. And we discovered that the gradient of F evaluated at x naught, y naught, z naught is perpendicular to the surface and hence perpendicular to the tangent plane. So our technique is just going to be to calculate the gradient of big F and then dot that with x minus x naught, y minus y naught, z minus z naught. Or in other words, the gradient of F is going to give us the vector ABC that is perpendicular to the plane. So this slide formalizes that. Hey, if you have a function big F that's differentiable, that has derivatives at the point P given by x naught, y naught, z naught on the surface big F equals 0, then you can find the equation of the tangent plane by using the partial derivatives big F with respect to x evaluated at your point. This is your A. The partial derivative with respect to y is going to be your b, and your partial derivative with respect to z is just going to be your c. In other words, the gradient of f gives you the normal vector that you need. And we said, hey, we looked at the special case where z was explicitly defined, where we had z equals f of xy, and we said that the gradient of f simplifies. You just need to calculate little f of x. The partial derivative of little f with respect to x at x naught, y naught for your A. Your B is going to be the partial derivative with respect to y, and then -1, because we identified that if we had an explicitly defined function, then the gradient, which usually looks like big F with respect to x, derivative of big F with respect to y, derivative of big F with respect to z, that this simplifies in the explicit case to just calculating little f with respect to x, the derivative of little f with respect to y, and we got a -1 in the previous video. So the calculation can simplify. So we'll show a couple of examples. So find the equation of the plane that is tangent to, I don't want to find the normal line, we're going to do that later. So find the equation of the tangent plane to the surface z equals x squared minus y squared at the point 3, 2, 5. And if we didn't mess up, we should be able to plug 3 and 2 in for x and y, and it should output that 5 for us. So 3 squared is 9 minus 2 squared is 4, 9 minus 4 is 5, so this point looks correct. And so what we want to recognize is that z has been explicitly defined, which means the gradient of f, which is perpendicular to the surface z equals x squared minus y squared at any point on the surface. The gradient of f has a simple calculation. We do little we do the derivative of f with respect to x, the derivative of our function right here with respect to y, and then -1. And the idea really is that when we have z equals x squared minus y squared, if we subtract the z from both sides, we get 0 equals x squared minus y squared minus z. And then this is our function f of x, y, z equals x squared minus y squared minus z. And so if we calculate the gradient of f, we're going to get partial derivative with respect to x for the first component, it's going to be 2x. Partial derivative with respect to y is going to be -2y. Partial derivative with respect to z is going to be that -1, which is the same thing that we would get if we just said, what's the partial derivative with respect to x? 2x. Partial derivative with respect to x is 2x. Partial derivative with respect to y, -2y. And if it's explicitly defined, you're always going to get a -1 in that third component position. So this is a special case of doing this right here, which is what we did in the previous video. And so the idea is then if we want the gradient at a specific point, we plug in our values for x and y. So the gradient of f at the point 3, 2, 5 is just going to be, hey, replace the x with the 3, replace the y with the 2, and replace z with a 5, but we won't need to in this case because we're never going to wind up with a z in any of the components. So we get the gradient of f is 2 times 3 is 6, -2 times 2 is -4, and right here I get a -1. So this gradient vector is perpendicular to our surface and therefore perpendicular to the tangent plane. So our tangent plane formula is going to be given by 6 times the x component times x minus x naught, but my x naught is 3. You choose the point on the plane, plus the -4 times y minus y naught, and y naught is equal to 2, the point on the plane, plus -1 times z minus z naught, but z naught is equal to 5, and this is a dot product that needs to equal 0. So this is the equation of the plane. I could put that as a minus, the plus, the negative could be rewritten as a minus 1 times stuff. I don't need the 1, and this is good. And we could also choose to do this. We could choose to distribute the 6 in, do 6x minus 18 minus 4y plus 8 minus z plus 5 equals 0. Add z to both sides. Add the constants. Minus 18 plus 18 is minus 10. Minus 10 plus 5 is minus 5. So we'd get 6x minus 4y plus, what did I say, plus minus 5. It was minus 5 equals z. So we could put it in this form. You could also, if you remember, the form, it could also be ax plus by plus cz plus d equals 0. So another way to do it is to replace the a, the b, the c with the gradient components, and then plug the 0.325 in and solve for d is another way of getting at this. So another example, so in this case I have an implicitly defined relation or surface in space. So in this case what I want to do is subtract that 9 from both sides. So I want to get the surface f of x, y, z equals, and what you're doing is taking the x squared plus y squared plus z squared, subtracting 9 from both sides so that you get this stuff here equal to 0. And then you let big F be the stuff on the left, so you let it be the x squared plus y squared plus z squared minus 9. And now you have a gradient, you have a function big F equals 0, so the gradient of big F will be perpendicular to the surface. So you can calculate the gradient of f. The gradient of f is going to equal the partial derivative with respect to x is just 2x. The partial derivative with respect to y is just 2y. The partial derivative with respect to z is just 2z. And we want the tangent plane, the plane that is tangent to the surface, at a specific point. So we want to calculate the gradient of f at that point. And the gradient will be perpendicular to the surface and thus perpendicular to the tangent plane. So now we just plug in 2 times 1, 2 times 2, 2 times 3. Replace the x, the y, the z with the appropriate numbers, and we get 2, 4, and 6. And here's where you have a little bit of a subtlety. This vector is perpendicular to the surface. So one thing that we could do right away is just construct our tangent plane. We could say our plane is going to have, right, these are our A, B, C. This is our vector A, B, C that's perpendicular to the plane and perpendicular to the surface that we started with. So what we could do, but we don't need to, I'm going to show you that we don't have to do it this way. What we could do is do now 2, there's our A times x minus x naught, but x naught is 1. This is our point x naught, y naught, z naught. So do x minus 1 plus 2 times y minus y naught is 2 plus 6 times z minus z naught is just 2, and this dot product has to equal 0 because I'm taking the dot product of perpendicular vectors, and this works. There's nothing wrong with doing it this way. However, what I could notice is that this perpendicular vector, this vector that is perpendicular or normal to my surface, can also be written as 2 times 1, 2, 3, and realistically you only need a vector ABC perpendicular to the surface. Any perpendicular vector works. So if I factor out the 2, I can start off with a smaller perpendicular vector. I could go 1 times x minus x naught plus, I did 2, 2, that should have been a 4 right there. That's a mistake. This should be 2, 4, and 6 coming from my vector 2, 4, and 6. Those are my A, my B, my C in the plane formula. And so when I factor off the 2, I get 2 times y minus 2 plus 3 times z minus 2 also needs to equal 0. So I can use the shorter vector if I notice that there's a common factor in the components. If all the components are negative, I could factor a negative out. So I can use factoring to make this vector still perpendicular to the plane and the surface, but smaller in length. And notice you'd get the same result just by taking and dividing both sides of the previous equation by 2. You would simplify the calculation down to what you see right here. So I usually look at my normal vector and I see if I can reduce its size through factoring, and then I'll use the reduced size vector. The other thing to be aware of then when you are looking at an answer key, you want to be aware of the fact that there are going to be infinitely many ways to describe a tangent plane. So if I take this and multiply it by any scalar, say I multiply it by 10, I get 10 times 2 is 20, 10 times 3 is 30 equals 0. So the answer key might have something that looks different than what I have. So I need to pay attention, is the answer in the answer key just a scalar multiple of the equation I have for my plane? And if it is, it means you have equivalent results. So it's just something to be aware of.